Navidad. Feliz Navidad. Oh, sorry. You were recording that? Please don't tell me you were. Hello, everybody. My name is Isaac Bear from Bear Science Lab. And today, we're doing Riemann sums. Now, I don't blame you if you don't get this on first watch, because Riemann sums are really difficult to understand, especially the formulaic approach. I was like looking at my notebook and then looking at the instructions.
Is there any difference between Riemann sum and 2 plus 2?
Shut down. Okay, so Riemann sums are like an approximation. I don't need you to talk.
Okay.
Did I ask? So, it's like an approximation. Oh, I said approximation. It's like an approximation of an integral. And it is necessary when you aren't given the function, and instead, you're only given like a table of x and f of x. Now, Riemann sums can be done in two ways: the sketch, which is the boring way, and the formula, which is also the boring way. So, what does that mean? Well, what do we mean by approximation of integrals? Well, if you're here, you probably already know that integrals, or antiderivatives, are known to be the area. Then, all this crap under here is the integral. No, that's not how you draw the integral sign. The integral of f of x. And this kind of integral is called a definite integral, which has a value. An indefinite integral, how do I explain it? If you have an indefinite integral, like for example, if f of x was equal to the derivative of tiny f of x, then the integral of f of x would be, big F of x would be tiny f of x. Alright, I think I've gotten to the point here. It's basically just the derivative, but backwards. And you also add funky plus c at the end. Alright, so now how do we approximate these? Well, look at these again. We can use rectangles and also trapezoids, but we'll get to that later. So, let's say we have a function like this. How can we approximate the area from 0 to, let's say, over here using the Riemann sum? Well, the answer is it depends on how many intervals you're using. So, what do I mean by intervals? Well, let's draw some funny-looking little rectangles, boys. So, let's draw it. I think this is called left-handed. No, it's called right-handed, because right-handed is the under approximation. So, this is where we wanted to stop. So, this is calculating, or at least approximating, the area under a curve using 5 rectangles. Now, what do you think would happen if we use more rectangles? So let's clear out the area under here and see what happens if we drew, say, 10. So let's say we have like skinny rectangle over here. Then we have another skinny rectangle. Then another skinny rectangle. Then another skinny rectangle. Then another skinny rectangle. Then another skinny rectangle. And I think you get the point already, but I'm gonna keep drawing skinny rectangles. But you can probably see that it fills up the space much better and is therefore most probably a better approximation of the area under the curve here. See? That fills up the space much more nicely than if we just did like 5 rectangles. I don't even know how many there are here. I'm not bothered to count, but whatever. Now, what is this? Well, I think that is called right-hand approximation. Why is it called right-hand? Well, do I know my lefts and rights? No, I don't. This is a left-hand approximation. Left-hand approximation. Why? Because you actually use the left vertice of the rectangle to go on the curve. Over here, it isn't so much the left-hand rule anymore because I drew it inaccurately. But if we were to draw this for the left-hand rule, then we would draw it a little something like this. Then over there, then over there, and over here. Good, right? All right. So, what does a right-hand approximation look like? Well, I'm not going to draw that many rectangles because I don't have the time for that. Instead, let's take this function, go until here, and the right-hand approximation is when the right vertice of the rectangle is placed on the curve. Now, usually you want to do these while knowing what your intervals are. And what is this interval nonsense I've been talking about anyways? Well, after I finish drawing this right-hand thing, then I'll show you. The intervals are these little spaces between the rectangles. So, the interval can also be denoted delta x. And the smaller the interval is, the more accurate this approximation is, as you saw before. The skinnier the rectangle was, the better approximation of the area there was. Okay, so if one of these is delta x, then what is this? Well, what can I call these? Well, I'm going to be very creative with the names and call it delta x, 2 times delta x, 3 times delta x, and so on. So 3, 4, 5, 6, and 7. Because that's that. So now, what are all these delta x's, melta x's? Well, the thing is, how do you calculate the area of a rectangle? Just tell me again. You take the base.
Bitch.
Good job, buddy. And you multiply it by the height. So now, our base will always be the same because our interval must be constant when it comes to Riemann sums. So our base will always be delta x. And our height, well, that differs between the left-hand rules and the right-hand rules. So, for the right hand versus the left hand, oh yeah, and there is a midpoint in between that I'll show you probably in the next video, but not right now. Okay, so what is left hand versus right hand? Well, here you might notice for the left hand that you're taking 0, then delta x, then I guess I can say it as f of x to the I, while this is f of x to the I plus 1. I don't know how to describe it, man. So, now, let's try to understand what the midpoint is. Well, the midpoint rule is when you take a function. Oh yeah, I should probably put something right. So the midpoint rule is when you take a function, yep, good. And then, so write midpoint here. You split it up into intervals. So here is, let's call this x1, x2, and oh, now I know what I can say here. x3, x4, x5. If I call these x1, x2, x3, x4, x5, then these actually do apply. Okay. So now, let's just do this. This is the value of xi. This is xi plus 1. This is xi. This is xi plus 1. All right. Let's get started with this. So, here, let's get a better look at this. Let's draw a little line over here at x1, and then the y-axis helps us for x0. Then, let's take the midpoint, and I guess it's right there. The value of the midpoint is right over here. And then, we draw a rectangle there. Alright, now let's do that with x2. This is kind of tiresome, but in the next video, I'll show you a formula that makes this easier. So, here is another rectangle, and I think you get the point, so I'll just show one more. So, here it is. So, now, there's also a trapezoid rule, but I'm not going to show that to you. We will save that for next video. So now, here is the formulaic way of understanding these things. To get the area of something with the left-hand rule, then we would use, how do I say this? Oh yeah. We would take delta x times the sum of fx1 plus fx2 all the way until f of xn, n as in how many intervals there are. So, for example, there are 7 intervals here. This is x7. So, this is how you would calculate it using the left-hand rule. And actually, no, I'm just kidding. Not like that. You would use fx to the n minus 1. For the right-hand rule, you would use the same thing, but you have, you don't have x to the 1. You have x to the 2. You know what? Maybe that makes it harder to understand, so I'll shift everything over. So here you have f of x to the 0 first, then here you have fx to the 1 first, then here you have x to the n minus 1 first, and then over here you have f of x to the n last. You can go in there if you want.
No.
I know you're tired.
No, it's fine. Go.
You can sit down. Okay, so now let's try to get more formulaic understanding of this crap. So what do we do here? Well, how can I express this? Let's say we wanted a really accurate estimation of a function. So, let's say, for example,
I can estimate a function. For example, 2x is equal to
what the hell, man?
5. X equal to 3.
Did I ask for his input? No. Did he give an input? Still, yes. Okay, so what we're going to do, so we're going to try and take the integral of, and you know what, I actually might have to erase some stuff over here. So make sure you've taken down these notes. I'll keep these up for the slackers. Alright, so now, the integral, let's say we're trying to calculate the integral from 0 to 6. Trust me, the 0 will make your life easier. Of not f of x. 9x squared plus 3x cubed. Now, the really ugly thing here is that, what if we wanted to use, like, not 5 or 6 rectangles where we could easily make a sketch? Not easily, but we could still make a sketch. What if we wanted, say, 100 rectangles? That would be absolute torture to sketch. Or maybe even 1,000 rectangles. That's not humanly possible to sketch. What if we wanted a very good approximation, and so we made x very high? In this case, let's keep it at 1,000. Well, my amigos, how do we calculate delta x? Well, it's equal to the interval we're integrating on, divided by, wait, no, this is not delta x. This is the number of intervals, which we'll mark with I, divided by the amount of intervals, I. So, in general, if we had a b of f of x dx, then the number of, over here, we would get b minus a over I, the amount of intervals. So in this case, that's 6 minus 0 over 1,000, or 6 over 1,000, which I don't want to calculate in my head because I'm lazy. Oh wait, no. I know what it is. It would be 0.006. So now, what do we do? Well, what we're going to do is this. Let's say we're doing it via the left-hand rule. And we'll also do it by the right-hand rule for good measure. So for the left-hand rule, we can actually come up with this formula. From I equals 1 to I equals, well, in this case, 1,000. We can have f of x to di. Good, right? And then for right hand, we have the same thing. I think I explained this kind of stuff earlier. I1, I2 equals 1,000, and you multiply it by delta x, which I also explained earlier. Let's go. So, now for the right hand, you do the same thing, but with xi plus 1. Alrightos, let's begin. So, to do this, what we have to do is a little something called trickiness. What if let's say we had x0 equals 0, for example. And then we had, okay, how to explain this? Let's say we have 8 intervals over here. So here is 1, 2, 3, and 4. Let's say we wanted to make 8 subintervals. This would be x1, x2, x3, x4, x5, x6, x7, and x8. It would be pretty clear by just reasoning that, for example, x6 is 3.5, but what if we wanted to find a new derivative? Well, to find x to the, for example, I plus 1, to find x to the I, for example, we simply take this. We take the formula x1 plus, well, not x to the I guess x to the n, because it's any number, x to the 1 plus n minus 1 times delta x. I believe so, anyways. Yeah, I think so. So, now, for example, let's say we wanted to calculate x6 or x4 here. Well, that would be x4 times x1 is 1 plus n minus 1, 4 minus 1, delta x is 1/2. So it's 1 plus 3 times 1/2, which is 1 plus 1.5, which is 2.5. And we can pretty easily see just by sight, use your eyes, boys. We can pretty easily see just by our basic reasoning that this is equal to 2.5. So now, using this reasoning, can you come up with a way to express x to the n plus 1? Well, we can express that like this. N plus 1 minus 1 times delta x. And this is actually redundant because we can simply make this n delta x. The context of the sigma, we're going to have to make that I. So, let's erase this and just keep those formulas to the side. Xn is equal to x1 plus n minus 1 delta x. This is x1 plus n delta x. There's also a midpoint formula in this kind of shape, which is I equals 1 to I equals n of f of xi plus f of xi plus 1 over 2. But that's too lengthy for me to do right now, because this lecture is already way overextended. Let's just do left hand and right hand. So left hand, fx to the I. How do we do that? Well, that's essentially x1 plus n minus 1 delta x. Or, in this case, xi plus ni, no, not ni, plus I delta x minus delta x. Now, in this case, solving for xi, x1 will really do nothing because f of x1 is like f of 0. Plugging that in very simply gives you 0. 9 times 0 plus 3 times 0. 0. So then, x1 is 0, so xi would be simply n, or rather I delta x minus delta x. Now, in this case, we made delta x 6 1,000, but we'll plug that in later and you'll see why. So now, whoopsies, I may have made a mistake. I should probably make this 3x just for my own safety, because trying to cube this is going to result in my death. So, sorry, and fx, let's do this with the left-hand rule. You get or rather, let's do this on the left-hand side, I guess. So over here, we have...
You want to erase those?
No, because I want to keep them up. Okay. Over here, we have sigma of what? Well, we have sigma of I equals 1, I equals 1,000, and then spotting this right over here, we can say that we have I delta x minus x. So now, that's basically the same as plugging this in. Oh yeah, and then you gotta multiply that by delta x. Whoopsies! So, that's basically the same as plugging that in. Now, plugging and sucking, our formula was 9x squared plus 3x would give us, well, what is I delta x minus x whole squared? First of all, we would have to find that in order to do this. I delta x minus x squared would be a squared minus 2ab How did this x get here? It should be delta x. So I delta x, or I delta x squared, and then plus delta x squared. Okay, so just taking out delta x squared, we get I squared minus 2i plus 1, which I think can come in the form I minus 1 whole squared. Okay, so we have delta x squared, I minus 1 whole squared. So, let's actually have that expanded. I squared minus 2i plus 1. It'll help us later, I promise. Okay, so now we have... God, this is so long. Okay, so now we have 9 times this load that we just created. Let's just write it as a scribble. Can't fit that much text in there. And then we have plus 3x. Plus 3 times I delta x minus delta x. Alright, so now what we do here is we factor out all our delta x's and constants. So we can rate this up into what happens if we factor out the delta x squared and 9 delta x squared I squared minus 2i plus 1. Well, we get 9 delta x squared times sigma I equals 1, I equals 1,000. We can take out all the constants and stuff. Remember, delta x is a constant. So now, I equals 1, I equals 1,000. What is left? I squared minus 2i plus 1. Alright, and now, oh yeah, and we can actually split that up into this minus 2 times I squared minus 2 times this, and then plus 1. 1 is a constant, so it can't really get sigmaed. And then plus 1, and then we have sigma of, at the end, we have delta x on the outside, or rather 3 delta x on the outside, times I minus 1. Oh, I just realized it is a much dumber thing to not reduce this to I minus 1. Well, screw me. Let's make this I minus 1 squared. You'll see why shortly. It's pretty elegant. Trust me. So, now, I forgot the sum of squares. Okay. So, what is this at the end? Well, we get I minus 1. That the sum of squares is actually I times I plus 1 times 2I plus 1 over 6. Let's just keep that noted so I don't forget. Plugging in I minus 1 would give us I minus 1 times I times 2I minus 1. Alright. So that's essentially what we want to plug in over there. So this is simply (1,000 minus 1) times 1,000 times 2,000 minus 1. I'll just write that as 1999 because I don't have the space. And we divide that by 6. And then we multiply that by, we have plus 3 delta x. And then we have sigma I minus 1. And then we simply use Gauss's formula, I times I plus 1, which gives us I minus 1 times I over 2. So that's 999 times 1,000 over 2. And then we simply plug in our delta x's, and this is solved. And you can do that for any number of intervals. So that means that this is our formula for any number of intervals, and we can calculate the sum under the area of this curve for any number of intervals as long as we know the delta x. Let's go, boys.
Done?